guys, so we're starting chapter 16, which is acids and bases. This one will also have 3 sets of videos, and probably so will 17 just because of the amount of material we're covering. So I hope y'all enjoy. So this is just some basic information about acids and bases to start with. So acids are always going to have a sour taste. Also, they can dissolve lots of metals. That's something maybe you've seen in a James Bond movie. They can neutralize bases, and they will change blue litmus paper red. Some common ones are hydrochloric acid, acetic acid. Hydrochloric acid is kind of like our stomach acid. Acetic acid is just vinegar, which y'all have used already in lab. Okay, also sulfuric acid is pretty common. Citric acid is in citric fruits. And then we've got less potent ones like phosphoric acid, which used to be in soda. It's not as high of a content as it used to be, but there's still a little bit in there. Okay, so our carboxylic acids, these are the ones that have this COOH in there. So this group here, and that's an organic acid. It's common in acetic acid, citric acid, even malic acid, which is in grapes and apples. Bases, on the other hand, are going to taste bitter. Most things that are basic we don't ingest, but a common thing is coffee or tea. Caffeine is actually the base in there that makes it kind of bitter. Also, most bases are going to be cleaning products, and hopefully you've seen that baking soda is a cleaning product. You'll have used bleach, that's a cleaning product. Those are both bases. Okay, so they feel slippery. Also, they're able to neutralize acids, and if you notice here in the picture, they've got that little bottle in the front. It's to neutralize your stomach acid some, so like Tums do that, milk of magnesia, things like that are going to help try to cut some of that acid out of your stomach, and because you probably have too much at that time if you're feeling that way. Also, they will change red litmus paper to blue. And then some common bases, we've already talked about some, but sodium hydroxide, potassium hydroxide, sodium bicarbonate. So that's what baking soda is. That's what's in a lot of antacids. Ammonia, some of you use that to clean. Ammonia is also in like Windex. And then we've got sodium carbonate. All right, so for acids, I do want you to know, get used to this H plus versus hydronium. We are going to use them interchangeably, and this is very important because hydronium is just a H added to water. Okay, so most of the time I will write H plus because H plus is faster to write. But just know if water is present, it really is hydronium. Also, most of the times these reactions are going to happen in water, and so you're going to see them there as H3O plus, but you may not have to write them that way. So there are 3 definitions of acids and bases we're going to cover. We're really not going to cover this bottom one, Lewis definition, but Arrhenius and Bronsted-Lowry, you need to be very familiar with both of those. There are slides for each of them, so I'm going to go on. So the most common one is the Arrhenius acid and base theory. So for Arrhenius, an acid is going to produce H in solution. So what happens is an acid, it breaks apart into solutions, and then it produces all these H plus ions. Okay. A base is going to produce OH ions in solution. So again, when they break apart, we're looking at all these OHs. And this is the most basic definition of acids and bases. And again, this is Arrhenius. Just some things you need to remember from chapters 7 and 8. So neutralization reactions, that was in chapter 8, along with net ionic equations. Just remember it's going to be an acid, so it's going to have H plus, and it's going to be a base, it'll have OH minus. These two come together to make water, which is on the other side. And then salt is whatever's left. So any ionic compound is called a salt. Yes, that example there, sodium chloride is table salt, but any ionic compound is a salt. Okay, so after a little while, people decided that Arrhenius was too narrow of a definition, so that's why we got Bronsted-Lowry in their theory. Okay, so they say an acid is defined as an H+ ion donor. So it gives it up. Okay, but the base is an H+ ion acceptor. So now the acid definition is basically the same. It's not worded the same, but it means the same thing because here's our acid. It can give it to something else. But now you're going to need to have a space for the base to accept it. Okay, and as long as you have that space, it can come in there. Please note when you move these around, their charges are going to change because that H+ ion moved. Also remember to change your charges. Okay, some things for the acid base and conjugates, which we're about to discuss. Acids and bases, true acids and bases are going to be on the reactant side. So reactant. Conjugates are always going to be on the product side. Okay, and I do want you to notice the acid pairs up with the conjugate base, and the base pairs up with the conjugate acid. The way to tell what goes together is ignore the H, and everything else should be the same. Also notice in Bronsted-Lowry, it is defined as an H+ or H or donor or acceptor. So we're only moving one at a time, hydrogen. Just make sure you're aware of that. Okay, so here we're looking, look, the HCl and the Cl- go together, and then our water and our hydronium go together. Okay, and here our ammonia and ammonium go together, and our water and our hydroxide go together. So just make sure you're looking at those elements that are not H to see what goes together. Also, again, note the change in charges. Okay. Okay, you will have to be able to determine acids and bases and conjugates. So make sure you know what's happening with that. Okay, so here's our conjugate acid-base pairs. We're looking at the base becomes the conjugate acid, and the acid becomes the conjugate base, because all that's happening is a hydrogen is moving. And together, they're called that conjugate pair or conjugate acid-base pair. So here's that lining up like I was showing you before. So look, the hydrogen from the acid is moving to the base. Okay, so here we're just going to identify. So it gave us an example. So we need to identify what's the acid and the base. That's the first thing. This bottom one again is the example. So sulfuric acid or water, and sulfuric acid turns into hydrogen sulfate. So this is our acid, and that means water's our base. And we know that water's our base because on the other side, it's gained a hydrogen. And on the hydrogen sulfate, it lost a hydrogen. Okay, so similarly in this bottom one, we're looking for what's happening. We've got our hydrogen carbonate or bicarbonate, our water. And if we look, water is the acid this time because on the other side, it's missing an hydrogen. So that means that hydrogen carbonate is our base and carbonic acid is our conjugate acid. And again, make sure the acid and conjugate base pair up and the base and conjugate acid pair up. Okay, there are some more examples. If you need help, please let me know. Okay, now let's real briefly, we're going to talk about acid strength. This may be one question on our test or a quiz, so don't get bogged down on this. This does go back to electronegativity. So when electronegativity increases, your acidity will increase because it's holding on more. But hydrofluoric acid's a little different just because it's so small. So when the particles get bigger, also they're going to increase in acidity, and that's just because there's so far of a difference between them. Okay, and oxyacid, hopefully you remember this from chapter 4. We started naming, but y'all didn't really name acids and bases. This really appeared in chapter 8. But an oxyacid is just an acid with oxygen. Please note, the hydrogen is always going to be attached to an oxygen. And that's because of those hydrogen bonds. So the more electronegative the element, the stronger the oxyacid. If you don't remember the electronegativity trend, it looks like this. So fluorine is going to be the strongest in electronegativity. So chlorine, so it goes fluorine, chlorine, bromine, iodine, I believe. I'm not 100% on the bottom two, but fluorine is the most electronegative. Chlorine is next of the halogens. So chlorine is going to be a stronger acid than iodine. Sorry, it's going to be more electronegative. Okay, really the one I want you to know is this one, that the more oxygen something has, the stronger the acid's going to be. So that's the one I'm probably going to test. Okay, so just if everything else stays the same and the oxygens change, whichever one has the most oxygens, that one's going to be the strongest. Okay, so here's an example with our chlorate derivative. So we've got perchloric acid, which is actually a very strong acid. And then we've got hypochlorous acid, which is very weak. And so you notice the more oxygens it has, the stronger the acid. Okay, also Kas are going to come into play. We'll talk about that next video, okay, in part 2. Okay, and this is actually where we're stopping today. So I hope y'all enjoyed the video. Y'all have a good day. Let me know if you need any more help, okay?